The introduction of the material for section 5.4 is actually quite brief because we've already covered this content. First off, it is to recognize that an indefinite integral by the fundamental theorem of calculus part 1 actually does output an antiderivative of the integrand, as long as that antiderivative can be found. And we've already studied how to find antiderivatives for a variety of functions like we would see in this course. So what there is to talk about here with respect to indefinite integrals would be, well, what is it that makes it indefinite? The integral is indefinite if it does not have bounds. There is no lower bound, there's no upper bound. A consequence of that is that we are not interpreting an indefinite integral, therefore, as an area under the curve, a specific area. It is an indefinite integral represents a function, okay, that would tell us about the integral. That function is going to be an antiderivative of the integrand if we can find that antiderivative. And because we have yet to establish which particular function we are going to be using to represent it, we need to use the most general antiderivative anytime that we are referring to an indefinite integral. So the indefinite integral, the integral of f of x dx, is big F of x plus c, where the c is the arbitrary constant as we had seen previously. So you can refer back to the section on antiderivatives for how we can find the antiderivatives to a variety of functions. That is primarily by knowing the derivatives really well for many families, that as we have studied, and reversing the rules in a couple of cases. We reverse the general power rule, for example. In order to find then the antiderivative of a power function, we would in general add 1 to the exponent and then divide by the new exponent. So we get something like x to the n plus 1 over n plus 1, unless the exponent was negative 1. In the case where we had x to the negative 1, that was 1 over x, then the antiderivative was actually the natural log of the absolute value of x. And then we would add plus c for either of those cases. We also reverse the rule for the differentiation of an exponential function. So the derivative of b to the x was b to the x times the natural log of b. So we reverse that to say, well, the antiderivative of b to the x would be b to the x divided by the natural log of b. And so there we already have the ability then to find out what the indefinite integral would be for some exponential function. We also knew from the table the table of known derivatives of families how to find, for instance, the antiderivative to the trigonometric functions or the hyperbolic functions or the inverse trigonometric functions. We know we know the derivatives of those functions, that is, and therefore we know those to be antiderivatives of some other functions. The other thing in this section for us to look at is called the net change theorem. We've already discussed this as well, so more formally stating it here. The net change theorem can be represented by the fundamental theorem of calculus part 2. Since the integral can be the definite integral can be evaluated by using an antiderivative at the bounds, well, then we can consider that the integrand itself is the derivative of that antiderivative. And by that interpretation, then contextually, we are saying that when we are taking the definite integral of some function, we are finding the net change, that is the difference between the value at the end of the interval and the value at the beginning of the interval, the net change in the antiderivative function itself. An example where we looked at that already was when we did a definite integral of the velocity curve. The velocity function is the derivative of position. So another way that we could write this integral here is to say we're taking the integral from t1 to t2 of s prime of t dt. Right? Because s prime of t, the derivative of position, is another way to refer to the velocity function. And so when we take the integral of the derivative of position, we're going to get information about position because the integral gives us an antiderivative. And if we evaluate that antiderivative, it should be s of t2 there minus s of t1 here, then what we're actually finding is the position at the end of the interval minus the position at the beginning of the interval. And even if the object started at whatever position that it started at, okay, if it were to move forward and backward and forward and backward and forward and backward, something like that, when we're finding the difference between its final position and its starting position, that's actually the displacement of the object. Imagine this is moving back and forth, but along a line. When you do s of t2 minus s of t1, we're not finding the distance the object traveled. We're finding how far it is at the end from where it was at the beginning. That is the displacement of the object. When we integrate a velocity function over a time interval, we are calculating displacement, and we can refer to displacement as the net change in position. That is because it is the difference from the future position and the previous position. We talked about net change previously in this course, and most likely in your pre-calculus course as well, okay, by saying that net change is a difference in the output of a function. Like net change is f of x2 minus f of x1. So in general, you can think of net change as the rise of the rise over run when you're calculating a slope. It is the change in the y values over some interval. So that's what we're looking at here. The net change in position is what we get with the integral of velocity. Okay? In general, to figure out what it is that you're measuring from an integral, right? What the units would be for what you're measuring from an integral, you can find out by multiplying the integrand by the differential units, the integrand units by the differential units. For instance, in this case, we have the product of the velocity function and a differential representing time. So what are the units going to be for this integral? We're adding up what types of quantities? Well, if we multiply the velocity units, which would be distance per time, times the differential units, which are time, distance over time times time would just leave us units of distance. So we can interpret an integral of the velocity with respect to time. We can interpret that as if we are adding up a whole bunch of little distances. So this is going to, right, because this is a summation after all, right? So we're adding up a whole bunch of these products, and these products would tell us distances, right? Velocity times time is giving us distance. So we're adding up a bunch of distances. And we can continue moving ahead with that same idea in mind. As we are looking at integrals, we can interpret what the output of that integral is actually representing in context. So let's take a look at a couple of indefinite integrals here to remind ourselves of the rules of anti-differentiation, reversing the rules of differentiation whenever we can, and take a look at an example or two as well where we can interpret results from a definite integral through the net change theorem. So I'm going to refer back to the textbook here. Okay, I'll take this, I'll start with this first example right here. Verify by differentiation that this formula is correct. So they're showing us an indefinite integral. There's no bounds, right? And they're showing us the result of that indefinite integral is supposedly this. Notice we have a function of x plus c. So we have a general antiderivative. We must have the plus c there every time we do an indefinite integral. If you do not see bounds, you must put a plus c on your answer. It's a way that we can think about it from the start. It is important that we do that. We have a family of functions. We're finding antiderivatives here. In the section where we talked about antiderivatives, when we started applying them, we would apply them in cases whereby we would be given maybe some initial values. And those initial values would be values that would allow us to solve for a particular value of the constant. Okay. Here we're being asked to find the most general antiderivative. Well, actually, in this example here, we're being shown what that general antiderivative is. The truth is, to actually integrate this function to find this answer, you're going to need techniques from your future course. Okay, and that's going to be the case, in fact, for all of these. You would actually need some further technique that you can discuss in calculus too. So right now we're being told that this is supposedly the correct antiderivative for that integrand. And so let's check to see if that's true. Let's check to see if negative root 1 plus x squared over x plus c is the antiderivative to 1 over x squared, okay, root 1 plus x squared. Okay, so verify that the integral 1 over x squared root 1 plus x squared dx, just so we remember to put the dx in every integral you write, notationally that dx must be there, okay? we're also going to want to remember every time that we're missing bounds, we need to add a plus c to our antiderivative. All right, they have it written in this form, root 1 plus x squared over x. Okay, so since the integral of a function of x dx is equal to an antiderivative function plus c, okay, then our antiderivative function should be this, and that is, in order to check that then, the derivative of our antiderivative should be the integrand. So to check, let's take the derivative with respect to x of our output for the for the indefinite integral. Okay, here we go. So the derivative of this, and what is the derivative of that? Okay, we can use the quotient rule on the first term. Wouldn't matter whether I put the plus c here or not in this case, because the derivative of the constant is just going to be 0. We really just need to verify that the derivative of this variable piece right here is ultimately the integrand right there. By the quotient rule we have, well, first I'm going to leave the negative in front. Okay, we get low d high, so we get the lower function is x times the derivative of the higher function. The derivative of that numerator will require the chain rule. First we have the derivative of the square root. Remember, the derivative of a square root gives us 1 over 2 times that root, so 1 over 2 root 1 plus x squared. That takes care of the derivative of the square root. Then multiply this result by the derivative of its inner function. The derivative of 1 plus x squared is 2x. So we have low d high minus, now we need the high function. I'm going to put this out of the way. Okay. All right, I've already factored out this negative right here. I'm going to leave that in front. Okay, so the higher function is the square root of 1 plus x squared times the derivative of the lower function, so the derivative of x, which is equal to 1. Okay, so we've used the quotient rule over the lower function squared, so this is over x squared, and then the derivative of c is just 0. Okay, let's simplify this now, see what we can do. The negative, okay, I'll leave the negative out there for the moment. Okay, let's clean this up. We have, looks like I can cancel a 2 here with a 2 here. So we get x times x, which gives us x squared. So we have x squared over root 1 plus x squared minus root 1 plus x squared over x squared. So now we have a complex complex expression, I should say. Okay, fractional expression. So I have a fraction inside of a fraction. So to get rid of that, here's what I'm going to do. I'm going to multiply by root 1 plus x squared over root 1 plus x squared and go ahead and distribute that. That'll cancel it out right here, but then we'll multiply this by itself. Okay, I'll leave the negative out front for the moment. So we have now, what, x squared, because that cancels, minus the quantity, I need this parenthesis here for this quantity 1 plus x squared. And in the denominator we have x squared root 1 plus x squared. Okay, so now, okay, that's my drawing from the first page. So long. All right, now we're going to combine like terms, x squared minus x squared. So these are going to get to cancel each other out. We're left with a negative 1, and then distribute this negative back into there. We get a positive 1. So we get 1 over x squared root 1 plus x squared. And I believe that was the given integrand. Okay, so that is equal to f of x. So yes, this output right here is the true antiderivative. Okay, is an antiderivative to this integrand, and so therefore this would be the correct result of this indefinite integral. Okay, so we took a look at use of finding the antiderivatives by the power rule in the previous section where we did the fundamental theorem. But what about an exponential function? We haven't done one of those. So let's do this one. Let's take the indefinite integral of 2 to the x dx. So what is this equal to? We're going to get a function here. We need to recall how to find the antiderivative, okay, of b to the x, where b is greater than 0 and not equal to 1. Recall that the derivative of b to the x, that's where b is greater than 0 and not equal to 1, that derivative is equal to b to the x times the natural log of b. And again, we can prove that that's true by using invertibility, y equals b to the x, for instance, and then you can take the natural log. Okay, we can use invertibility of the exponential function and implicit differentiation. in order to show that this is true. So if the derivative of 2 to the x is 2 to the x times the natural log of 2, then the antiderivative, that is multiplying by a constant, is derivative. Then the antiderivative would be dividing by that constant. So 2 to the x divided by the natural log of 2. And then plus c must be there because we are finding the general antiderivative. And so that's how we find the indefinite integral for something like 2 to the x. Take a look back again at the book. Okay, so we have more examples in here. So we reverse the power rule. We can reverse the exponential rule. If you're given something like a quotient, right, they all have the common denominator of x, so you can divide each term by x. So you write this as 1 over x plus root x over x, which simplifies as 1 over root x, plus x over x, which simplifies as 1. And then you can find the antiderivative term by term. Find the antiderivative term by term. The antiderivative of 1 over x is the natural log of the absolute value of x. The antiderivative of 1 over root x, that would be the antiderivative of x to the negative 1/2. You add 1 to the exponent, that gives us exponent 1/2, and then divide by the exponent. Dividing by a half is the same as multiplying by 2. So for the second term, the antiderivative would be 2 times the square root of x. And then the antiderivative of 1 would just be x. So we have natural log of the absolute value of x, plus 2 times the square root of x, plus x, and then plus c for good measure. Right? So that we make sure that we have that arbitrary constant at the end. Okay, so that's the answer that we would get for that. Okay, what is the antiderivative to something like 1 over x squared plus 1? Which function has 1 over x squared plus 1 as its derivative? The answer to that would be from our table of known derivatives. This is the known derivative of the arctangent of x function. So if we wanted the antiderivative for this, the indefinite integral, we would have first, by the general power rule reversed, x cubed over 3 plus x, because x is the antiderivative of 1, plus the arctangent of x, and then plus c. Antiderivative of the sine, remember that the derivative of sine is cosine, right? But the derivative of cosine is negative sine. So the antiderivative of sine would have to be negative cosine. Because the derivative of negative cosine is negative sine. So antiderivative of sine of x is negative cosine x. But the antiderivative of sinh of x is just positive cosh of x. Recall the derivative of cosh is sinh. And then plus c. Negative cosine x plus cosh of x, and then plus c. Here we have a quotient contained inside of a square. What should we do? First thing, let's try to simplify it. How about writing this as 1 over r plus r over r? That's 1 over r plus 1. Then FOIL to expand it. Let's try that one out. Apply a little algebraic technique here. 1 plus r over r quantity squared dr. Okay, so we'll apply some algebra here. First, we're going to write this as 1 over r plus r over r quantity squared dr. That's the integral of 1 over r plus 1 quantity squared dr. Okay. Now, this would require a reverse of like a chain rule here because we have a function inside of a function. We haven't talked about that yet. Nor would we want to go down that route if we had a simpler method, and we do. Expansion here, doing a little more algebra. So let's FOIL this out. So first, 1 over r times 1 over r is 1 over r squared. And then we have 1 over r plus 1 over r, which gives us 2 over r. And then 1 squared, which is just 1. And now we can go through and we can integrate this term by term. To get set to do that, I'm going to write this as a power function. 1 over r squared is r to the negative 2. 2 over r can be written as 2r to the negative 1. Okay? Or in other words, you can factor out the 2. It can be 2 times 1 over r, because we know the antiderivative of a 1 over r type of a function, or 2r to the negative 1. And then plus 1 and then dr. Let's find our antiderivative. For the power rule, where the power is not negative 1, we add 1 to that exponent and then divide by the result. Adding 1 to negative 2, okay, so here's what it's going to look like. Negative 2 plus 1 divided by negative 2 plus 1. Right, and then we'll simplify that. Here we leave the 2, factor that out, and then the antiderivative of r to the negative 1, right? That's where we use the power rule for the special case, that gives us the natural log, but the natural log of the absolute value of r. It's very important we put the absolute value there, particularly with our indefinite integral, because we have not yet chosen any bounds, and we don't know if those bounds might be within the domain of the natural log function or not. We need the absolute value. That's in case we are allowed to choose values of r that might be less than 0, in which case we really would need these absolute values. So we must keep the absolute values there in case we might need it for whatever we're going to do with this function. Okay, the domain of the integrand must match the domain, okay, of the antiderivative as well. And the antiderivative for 1 with respect to r, that would just be plus r. And then we need a plus c there for an arbitrary constant. Let's simplify this. R to the negative 2 plus 1 is r to the negative 1 divided by negative 1. So we have negative r to the negative 1, or negative 1 over r, plus 2 natural log absolute value of r, plus r, and then plus c. And we can of course check. How can we check our answer? We can check by differentiating. Okay, we can check by differentiating our function here. We should see that big F prime of r here, the derivative of this, is equal to little f of r, which was the integrand. So the derivative of our result should equal the original integrand. Okay, we'd have to reverse our algebraic simplification techniques as well in order to demonstrate that that's so. Alright, so it's exercise in antiderivatives. So check again on your antiderivatives as we saw in a previous section. And also let's take a look at some net change type examples as well. Okay, here's a couple down here. Okay, suppose that the current, the current is the change in charge, okay, through a point on a a wire. You can think of it as like current in a stream, except if it's current in a wire, it's the it's essentially theoretically the electrons that are moving right through the wire. So the current in the wire is defined as the derivative of the charge, that is the change in the amount of charge. So if Q of t is the amount of charge that there is at a particular point, the rate of change of that charge with respect to time is how fast the charge is changing. That would be the current. Okay. What does this therefore represent? That's a 1 right there, isn't it? That should be an I. That should be I of t right there. All right, so that's because that's supposed to represent current right there. So if current is the derivative of the charge, then what does this represent? Well, Q prime of t has units of, okay, Q prime of t has units of charge per time. And if we take charge per time and multiply it by the differential representing time, charge over time times time would give us units of charge. So we would be summing up bits of charge from where the time is equal to A to where the time is equal to B. So this would represent, therefore, the net change in the charge over the time interval from A to B. Okay, let's write that out over here. Okay, so we have electrical current I of t equals Q prime of t, okay, is the rate of change in the charge Q of t, right, with respect to time. In other words, how fast is the amount of charge changing? So then interpret this integral. Okay, the integral of the current with respect to time. Well, that would be the integral from A to B of Q prime of t, that's the rate of change of charge with respect to time, times units of time. All right, if we consider the units for this product right here, the units are going to be the amount of charge per time times the amount of time. And so those units are going to be the amount of charge. Okay, so when we evaluate the integral, we are summing up the amount of charge. Okay, so this integral is going to give us the amount of charge, Q, at time B minus the amount of charge at time A. In other words, that is the net change, okay, the net change in the amount of charge over the time interval A to B. That would be our interpretation by the net change theorem for what we found here. So let's take a look at this one more example here. 57. If x is measured in meters and f of x is measured in newtons, and newtons is a unit of force. It's a kilogram times meters per second squared. Kilograms are mass units, and meters per second squared would be units of acceleration. So 1 newton would be a unit of force representing 1 kilogram at 1 meter per second squared. So newtons are units of force. Okay, but what are the units going to be for this integral right here? If f of x is measured in newtons and x is measured in meters, well, if x is measured in meters, then dx, which is a little change in x, dx would be also measured in meters as well. So you have f of x is newtons, dx is meters, and when you take the product of the two, you get newtons times meters, or newton meters. And newton meters, it would be units of energy as well, by the way. Okay, so this would be measuring an amount of energy over a displacement interval. Notice the units of the bounds here in our integral, all right, they're units of the variable x, and x is being measured in meters here. It's not a time integral here. It's a spatial integral. So we are saying from the position where x equals 0 meters to where x equals 100 meters. In other words, if an object were displaced over 100 meters, then this integral is telling us how much energy would be required, because it's going to be telling us the amount of newton meters. So newtons times meters would be the units. Another name for that would be joules, and that is a measurement of the amount of energy. Okay, so we have, if f of x is in newtons, and newtons those are units of force, that's kilograms times meter per second squared, mass times acceleration, force equals mass times acceleration, so newtons are units of force, and x is measured in meters, and of course that's a distance, okay, then the integral from 0 to 100 of f of x dx, okay, would output the net change in energy, that would be the newton meters or joules, the net change in energy on the space interval 0 to 100. This is not a time interval. All right, this is an interval of space because x is the amount of meters. Okay, the unit analysis for the integral, we have the units f of x dx. All right, well, we have that f of x gives us newtons, and dx gives us meters, so we end up with newton meters, which is again a measurement of energy. Okay, so this is really a work integral. The work integral is telling us how much energy it would require for us to complete a task. And work is is a measurement of the transfer of energy. So if we wanted to expend energy to move an object 100 meters, to displace an object by 100 meters, okay, the amount of energy we would have to expend is going to depend on the amount of mass that there is, and the amount of acceleration, and therefore the amount of force that would need to be applied, as well as the distance over which we wanted to apply that force. Okay. And so that is it for this section of 5.4. We refer back to the section on antiderivatives, where we learned how to do that. We are now able to apply it to these indefinite integrals through the fundamental theorem of calculus, which part 1 of the fundamental theorem of calculus told us that an integral as a function was going to be an antiderivative. Remember to put the plus c on there for your general antiderivative. Okay. And the other thing is to just, to recognize that by the net change theorem, take a look at the units that you get out of your integrand and pay attention to the units for the differential as well. Okay, the units for the differential are the same as the units for the bounds, because these bounds, A and B, have to be quantities for the variable of integration. Right? They're related to each other. Okay. So if we're integrating with respect to time, then the bounds would have to be measurements of time. If we're integrating with respect to space, such as x, distance, okay, then the bounds would have to be measurements of distance. So in doing a unit analysis, you can better interpret what the output of an integral is trying to tell you in a sense of an application. All right, that's it for this section. So check out the homework. You have about 10 problems or so to do in the homework for this section. Let me know if you have any questions. Take care.